Okay, hello students. In this video we're going to take a tour of the control box for the optical pumping apparatus. You can see it in front of you here and it looks quite complicated. There's a lot of connections and a lot of dials on it, so let's go through the most important elements of it so you get a little handle on how you control the optical pumping experiment. So we'll start down here just for a moment. I'll actually start with these connectors right here. This red and black jack is labeled vertical field. This is the current supply for the vertical Helmholtz coil that was pointed out in a previous video. This just simply is a current source that feeds the vertical Helmholtz coil, and there's a knob right here at the top labeled vertical magnetic field. So if you turn this knob, it allows you to control how much current is sent to the Helmholtz coil. So right now the knob is set at about 2.4, and what we found in the laboratory at the moment, setting it at 2.4, which I believe corresponds to 0.24 amps going to the vertical Helmholtz coil, this optimally cancels the vertical component of the Earth's magnetic field in the laboratory at the moment the way everything is described. So this can vary from quarter to quarter and location to location, but at the moment we feel like this 2.4 setting is injecting enough current to cancel the Earth's magnetic field. So that's what that connector is for. Like you might guess also, like there's current control for the vertical Helmholtz coil, there's also current control for the horizontal Helmholtz coil. That's this jack right here. So it's connected and all ready to go, but for the experiments that we do, this current is always set to 0 via this knob right here. So this knob is turned full, counterclockwise, it's at 0. So it's connected, ready to go, but we just don't use it in this particular experiment, in the experiments that we do here, okay? The next one over here is some connections to the detector, that light detector at the very end that detects the eventual light that makes it all the way down the optical rail. This is the power for it right here. It's called preamp power, so it's powers the detector down there, and preamp implies a preamplifier stage, which indeed is there, that amplifies the small light signal that's detected by the raw silicon photodetector in there. And then there's a detector amplifier output right here. This is the nice boosted signal that comes from the preamp on the detector, and that's typically sent through this cable to the oscilloscope for detection. And just below it here on this connection here, this is coming from the detector over on the optical rail here. So the small signal that comes in from the detector is sent in here, amplified, and then sent to the oscilloscope for processing. So that sort of covers all of these jacks right here. There's one in here that we're not using as a way of monitoring the current in the horizontal Helmholtz coil, but because we're not using it, I won't even discuss it. So that sort of handles all of these elements right here. So we're making some pretty good progress at the moment. Okay. Moving over here now, we get some connectors that are a little bit more important to us, and let me sort of describe what they are. This is labeled horizontal magnetic sweep field, or horizontal magnetic field sweep. As I mentioned, the horizontal field in the optical pumping apparatus is swept from some zero current up to some higher current, and so what that means is the magnetic field in the horizontal Helmholtz coils will also be swept from something like 0 B field up to some B max that corresponds to some I max, some current max that was supplied by the sweep. So it's just a constant time-dependent signal that goes from 0 to so many amps, back to 0, back up to so many amps, back to 0, back to so many amps, and that causes the magnetic field in the horizontal Helmholtz coil, as I said, to go from some 0 B field to some B max, from 0 B field to some B max. It just keeps doing that over and over again with a time constant that we're able to set ourselves. That's sort of what this section of the control box controls. And as you can see here, there are two connectors here that go out to the horizontal Helmholtz coils. There's an additional set of wire wrappings just on the horizontal coils that are fed by these two lines right here, and that's the sweep, the current that goes from 0 to some maximum, 0 to some maximum. That's on these lines right here. This monitor right here is actually just connected to a 1/2 ohm resistor that the current to the horizontal sweep magnetic field passes through. Why is that useful? Well, it's a 1/2 ohm resistor, pardon me, it's a 1 ohm resistor, not a 1/2 ohm, it's a 1 ohm resistor. So if we just monitor the voltage across this resistor here, this 1 ohm resistor, we can use Ohm's law to know what current is going out to the horizontal sweep. And if we know the current, we can calculate the magnetic field using the equation you'll find in the lab manual. So that's what this is here. This is just the voltage across a 1 ohm resistor. The 1 ohm resistor is in series with the horizontal sweep coil. And that's what this voltmeter is over here, just always measuring that voltage, and we can use Ohm's law to get the current. So it's very convenient. In fact, the voltage is the current because it's a 1 ohm resistor according to Ohm's law. Then we have something labeled recorder output. So this is a voltage that we can send to the oscilloscope that's proportional to the magnetic field that is instantaneously going through the horizontal sweep coils. The recorder output is calibrated. You can look in the lab man about the calibration. I think it's something like 5 millivolts for every 1 milligal, something like that. But please verify that before you go using it. And so the recorder output is a very convenient x-axis for our oscilloscope trace. So as long as the magnetic field is sweeping from 0 to some Bmax, 0 to Bmax, 0 to Bmax, 0 to Bmax, this voltage reflects that sweep, and we can send it to the oscilloscope. It's a very convenient x-axis for the oscilloscope in XY mode. So in fact, this on the x-axis and the light detector on the y-axis are exactly what our signal is going to be for optical pumping. We measure the output of the light detector as a function of the sweep magnetic field in the horizontal coils. So that sort of covers all of this. Lastly, moving on over here, we have the temperature here. So as I said, the rubidium cell has to be temperature controlled to keep the rubidium atoms in a nice vapor state. These wires here are a current that goes to the heater. This is a thermocouple sensor that comes back that tells us what the temperature of the rubidium cell is. And if you look up here, this number here is the temperature that the heater is successfully getting the rubidium cells up to, so about 52 degrees. So this part right here and this part right here, just the heater. And I'll just about end this video here on this last stage over here. We have the RF amplifier. So as you mentioned, there's that set of coils that we can apply an RF, something like 100 kilohertz or so, to the rubidium atoms. That's all done over here. So if we send an RF signal into this jack here from an RF generator that we have in the lab, so in fact we have one sort of our own right over here, you can see at the moment it's currently tuned to about 96 kilohertz. That's the RF that we're talking about, 96 kilohertz adjustable. If we send that into this jack right here along this coaxial cable, it'll get amplified, boosted up a bit, and the gain knob for that is right here. The RF amplifier, we can turn it up. We have it at about 3 or something. The RF comes in here, and this output here is what goes off to those reddish coils that were pointed out in another video. So that should pretty much cover all the connections in this lower half of the connector right here. In the next video, I'll cover the upper half.